Check this out. We've got something really fun today. This is so amazing. Oh man, again?
Let's review slope. What's the slope of this linear line right here? It's conveniently written in slope y-intercept form, so we can see that the slope is just 6. I'm going to use m to denote slope. The next one here is not written in a convenient form, so we'll do some algebra. How about take this and this to the other side? So we'll say 4y is equal to 5x minus 3. And then divide everything by 4, so we get y is equal to 5 over 4x minus 3 over 4. So we can see now in slope y-intercept form that the slope is 5 over 4. The slope of the line that passes through these 2 points. We have an equation for this. It's the slope is equal to y2 minus y1 over x2 minus x1. And we can call either one of these our first or second point. So it looks like this one's larger though, so I'm going to start off with this one, 19 as my y2. Next, this one will be my y1. Now we need to match it up so that if this one was my y2, this one will be my x2. So this is minus 3 minus 6. And this is 18 over negative 9, and that's negative 2. What's the slope of the x-axis? So the x-axis is completely horizontal, so the equation of that is y equals 0. So it has no slope, or the slope would be 0. The y-axis, now that's a straight vertical line, and the equation of the y-axis is x equals 0. So in here, we wouldn't really have an ability to measure the slope. So we would say the slope is undefined, and you might think of it as being an infinite slope. 1.1, limits. We want to find the slope of y equals x squared, our most basic quadratic. What are the problems? Well, the slope changes depending on the point or points that we're looking at. And what does slope even mean then? The first type of slope we'll be looking at is the instantaneous slope. That is the slope at one specific point on the graph. That would be an exact instant on the graph. And we're going to define that as the slope of the tangent for that point. Now, what's a tangent? It is a line that touches the graph at a specific part, and if you could zoom in super close, it would always be infinitely close. It would always be equidistant to the graph on either side. Now, whenever people define a tangent line as a line that touches the graph once, this is not a good definition. As you can see in this cubic, we have a point of tangency here, and a tangent line drawn from that, and sure enough, it comes over and hits the graph again. So careful with the definition of tangent line being a line that hits once. That's not the whole story. Let's find the slope of the tangent at the point 1, 1 for this same graph. Now we have the formula there, our slope formula, and we can put in one point at least, but we don't have another point. What would happen if we just used the same point twice? So 1 minus 1 over 1 minus 1. Well, this is not particularly helpful because then we get 0 over 0. And I'm putting it in quotation marks because we can't actually have this. This isn't an answer for us. And it's not helpful at all. To find the slope of a tangent, we're going to need 2 points for this formula to work. We will use a secant line to approximate the tangent line. A secant line is a line that passes through the graph. at 2 points. And we're going to approximate it at the point 2, 4. So this point here is 2, 4 and 1, 1. Let's see what the slope of that red secant line is. So our point here is 2, 4. I'll use that as my first one here. So 4 minus 1 and 2 minus 1. And that gives me a slope of 3. And I could have just seen that from the graph. I have a rise of 1, 2, 3, and a run of 1. So rise over run is 3. But this is not a very good approximation. It's actually, I mean, at least it's heading in the right direction. They both have a positive slope, but we can do better than this. So we want to just pick a Q that's closer to P, and then we'll get a secant that's a better approximation. So let's try x as 1.5. So that would be over here. Now, as soon as we do that, we're going to get a lot closer. So we're trying to draw the secant, see if I can do that. Something like that, okay. And that's a bit better. I mean, it's a better approximation to this black. It's still not very good, but we'll go with it. Now, if x is 1.5, then what's our y value? So remember, our equation is y equals x squared. So we just need to square 1.5. And that is 2.25, because you can think of it as 15 squared is 225, and then you just have 2 decimal places. Okay, so here's our equation. M is equal to 2.25 minus 1 and 1.5 minus 1. And in the numerator we get 1.25, in the denominator we get 0.5. Now we can clean this up. This in the numerator here would be 5/4. And this in the denominator, since I don't have a calculator, I'm converting it to fractions. This in the denominator would be 1/2, and 5/4 times 2. And simplify this, and I get 2.5. Now let's do even better than that. I'm going to snuggle right up next to 1 with 1.01. And this time I'm going to have to do this on paper here. 1.01 squared. And that's 101 and 00101. Not too difficult, but we got 4 decimal places here, so it's going to be 1.0201. That's my y value. Now we'll run through the same slope formula. M is equal to 1.0201 minus 1 over 1.01 minus 1, and that equals 0.0201 over 0.01. Multiply top and bottom by 100. That will be moving the decimal over 2, and we get 2.01 as our slope. So you can see that we started off at a slope of 3. We got closer and it became 2.5, and we got really close and we got 2.01. Now some students ask, well, why didn't I just jump to this right away? It's because I wanted to see a pattern. I wanted to see it getting closer and closer to something. If I just jumped straight to this one, then I wouldn't know if it was moving away from the 2 or moving towards it. So I'm trying to get a good pattern here to analyze. We moved closer and closer to P from the right. What about if we move closer and closer to P from the left side? So I picked a point here, 0.5, so it's half a unit away. 0.5 squared is 0.25. That'll give us the coordinate of our Q to make our secant line. And we're doing the same thing. M is equal to, and this time I'm going to put 1, 1 first because it's easier to subtract that way. 1 minus 0.25 and 1 minus 0.5. In the numerator, I've got 0.75, and the denominator 0.5, and this is equal to 1.5. You can change it into fractions if that helps. Next one, 0.9 squared is 0.81. And again, our slope formula here is m equals 1 minus 0.81 and 1 minus 0.9. And this gives us 0.19 and the denominator 0.1. Just move the decimal over or multiply top and bottom by 10. We get 1.9. And already we can see the pattern here, 1.5, 1.9. Let's see if we can get even closer though with a point 0.99. Now I'll just do a little bit of math here since we're not using a calculator. So 0.99 squared, and that would be 9 times 9, 81. 9 times 9 is 81 again, so 9. 0, and then it's just the same thing. And I've got to add those up. 8, 9. So it looks like, and then 4 decimals, so that would be there. Okay, so it looks like 0.9801. Using our same slope formula, 1 minus 0.9801, 1 minus 0.99. Gives me 0.0199 in the numerator and 0.01 in the denominator. Multiply numerator and denominator by 100 and we get 1.99. Let's see how this would look in real time using this interactive model. We have point P written here and it's going to stay here. Its coordinates is 1, 1. That'd be right there. We have Q set to the coordinates 2, 4. That would be up there. And we have the slope of the tangent. It's this black line here. And the slope of our secant is the red line here. And right now it's 3. So this is fun because you can move Q here closer and closer. And you can see Q's coordinates changing. And you can also see the slope of PQ getting closer and closer to the tangent as we get closer and closer to P. And then coming from the other side as well, we can see that the slope of PQ also gets closer and closer to the slope of the tangent as Q gets closer and closer to P. We can be pretty sure, given our numerical approach, that the slope of the tangent at this coordinate is 2. What is the equation for this tangent line? First we'll do slope point form, the sort of the underappreciated form of a linear line. And that would be y minus y1 is equal to mx minus x1. Now the point we know is 1, 1 and the slope is 2, so we just plug those things in. Y minus 1 is equal to 2 x minus 1. And we're done. This is an equation of the tangent line. And you might be thinking, yeah, wait though, why didn't we isolate y? Because this is slope point form, and we didn't have to. This is very nice. Let's go do slope intercept form. That would be y equals mx plus b. Our m is 2, so we'll plug that in there. And we know a point, x and y, so we're going to have to substitute that in here. So 1 and 2 and 1 again, and we don't know the y-intercept, so that's what we're finding here. And then we got 2 here, so minus 2 on this side, minus 2 on this side. That gives us negative 1. So it looks like our y-intercept is negative 1. Now we can go back and fill everything in we know, so y is equal to 2x minus 1. Now you can see that this took a few more steps. That's why I like slope point form. And it's probably more useful in this course when we're given a point and we're finding the slope. Now the slope of the tangent at point P is the limit of the slope of the secant line, PQ, as Q approaches P. So this is how we write it. LIM for limit, and we say what's moving where, so Q is getting closer and closer to P. This is the slope of the secant line, PQ. And the limit, if we could hypothetically go infinitely close to P, then we would get the slope of the tangent line at P. Now there just so happens to be a sneakier way to find the slope at this point for y equals x squared. So let's actually take a look at this. We've got our slope, and here's our slope formula. And we'll put in the point that we want, and that's 1, 1. Now we think of the equation that we're working with here, and we know that y is equal to x squared. So this y right here is going to be x squared. And this x here will just be x then. Now this is why this is a bit sneakier, and it works for this question because there's a removable point of discontinuity. When we factor this here, we get x plus 1, x minus 1. And in the denominator, x minus 1. And we see that we can take this out, and we're just left with m is equal to x plus 1. Now, what was x for this question here? It was 1. So we can put that in now, 1 plus 1, and we can get the slope as 2. Now again, this only works because we can remove this point of discontinuity here and plug in this value here. So this is kind of like what we were doing to find the coordinates of our point of discontinuity in 30-1. In this lesson, we should see that the slope of a tangent line at a point will be that point's instantaneous slope. And hopefully you can find the slope of a tangent line using a numerical approach. That means, just using values closer and closer to the point you want. Try these questions out from your textbook. See if you know what you're doing.